Welcome to this Maths Methods 3 and 4 revision video on Chapter 1 of the Essential Mathematics textbook, dealing with functions and relations. The questions and examples used in this video are taken from the Cambridge Essential Mathematical Methods 3 and 4 CAS textbook, and no intention has been made to infringe copyright, and my apologies if it has. This is simply a video resource for my current students to assist in their preparations for their VC examination. Thanks for your understanding. Okay. So I think this is probably going to be a fairly swift gallop through Chapter 1 because a lot of the information in there is sort of or should already be known. But to be fair, having looked through it now myself, I have learned some very interesting things. So a function, right? What is a function? Well, in its basic term, what I've just learned, or what I can pass on to you, is that a function is something that where you draw a vertical dotted line through a graph, it only crosses in one point, right? So if I have a circle, for example, here is my circle, and I was to draw a dotted line or a vertical line somewhere through that, because it crosses in two places, that is not a function. Something along the lines of a straight line, for example, if I draw a dotted line anywhere through or a vertical line anywhere through, I find out that that only crosses once, and that is a function. Functions can be restricted, right? So there are such a thing as restricted functions. And what is a restricted function? Well, it's where you only draw part of the graph. The graph here, this straight line here, actually goes on to infinity and beyond. But we tend to limit it within the confines of a set of axes, all right? Or we limit what we call its domain, right? Now, the domain is simply the x values that are permitted to go into the function. Right? Now, in many cases, we would suggest that most functions could have a subset of the real numbers could go in. Right? But if we try and restrict that function, then we will only put certain values in and consequently expect certain values out. So if we have the function of x, for example, x squared, and then we add a comma, and we say minus 1 is less than or equal to x is less than or equal to 1, then what that actually means is that we will draw our x squared curve, and the only values we will go down to is negative 1, and the only values we'll go up to is positive 1. My apologies for the wonkiness of this curve, or in fact this graph, but I think it's pretty much going to be the same throughout the whole of this video. It's here just to give you a general idea, right? Sometimes one of the things you're asked is whether a function is one-to-one or many-to-one. One-to-one. Now, in its basic form, what it's suggesting is it's one-to-one if every x value has a unique y value, or more importantly, every y value has a unique x value. So let's have a look at a couple of examples. What if we go back to our nice trusty, let's say y equals x squared? Does every y value have a unique x value? Well, one of the quickest ways we can look at that is a horizontal line, because, oh, there you go, I've got a y value there and a y value there, but they seem to have completely different x values. So this is not a one-to-one, right? It's not one-to-one. This would be called a many-to-one, right? Because there are many x values for each y value. And so I suppose it would be fairly sensible to assume that if I have a straight line looking like that, and I was to draw a horizontal line through it, then for my y value, I only have one x value, and that is a one-to-one function. So a vertical test will tell you whether it's a function, and then you can subset that into a one-to-one or one-to-many functions by doing the horizontal test. Now, something that comes up a lot in the exams is the concept of implied domains. All right, an implied domain. Now, this also seems to be called a maximal domain. Right, so as usual, Barry's been at it again. All right, whereby he's like, well, why call it one thing when we can call it 27? That magic number. An implied domain is pretty much where you think a function can or cannot have a domain. If we look at the idea of a function of x is equal to the root of x, then we know, firstly, that cannot have any negative values. right? We cannot square root a negative. And so what does that suggest? Well, if we look at our graph, which pretty much does something like that, what we can see is the smallest value that's going to go in our x, remember domain, right? It's got the word domain in the title, right? So we're looking at domain, so we're looking at the x values that can go in. The smallest value would be 0. Can it include 0? Yep, so we do that square bracket. And what's the largest value? Well, theoretically speaking, it's going to be up to infinity. And because we can't include infinity because it's more a concept than a number, we put this curvy bracket. How's that useful to us in questions? Well, ultimately, if you are given an example of this function, then are there any values? I suppose one of the things we can test for is what values would this not work for? Well, one of the great things is we know at the bottom of a fraction that value cannot be 0, right? It can't be 0. Anything divided by 0 is undefined. So if we know that 2x minus 3 can't be 0, then if we find the value of 2x minus 3, or what value of 2x minus 3 gives you 0, or in this case 3 over 2, then we now know that pretty much every x value is possible to go in here. We can put any x values in here, be it positive or negative, but not 3 over 2. And how do we write that? Well, basically we know that the domain is all of the real numbers, but not including 3 upon 2. All right? So that trick of looking at what can't be is quite useful to us. If we look at the idea of g of x is equal to the root of 5 minus x, we know that 5 minus x can't be less than 0. So let's look at the values of 5 minus x that give us greater than 0. Well, what does that give us? Well, minus x is greater than or equal to negative 5. And then if you multiply by a negative, what you have to do, you have to switch your inequality sign. So what we're saying is that any value, what we notice is any value of x that is less than or equal to 5 will in fact make this work. Any values greater than will turn it into a negative. So we can see that our implied domain, or our maximal domain, will be from negative infinity up to and including 5. Because we can have 5, because 5 minus 5 is 0, and we can find the square root of 0. And let's just do one more example. If we have h of x is equal to the root of x minus 5 plus the root of 8 minus x, well, the same thing. We're looking for situations. We know that this can't be 0 and that can't be 0, right? Neither of those can be 0. So if we look at the ideas that, all right, well, we've got to make sure that x minus 5 has got to be greater than or equal to 0, and the same with 8 minus x has got to be greater than or equal to 0. That gives us x has got to be greater than or equal to 5, minus x is greater than or equal to minus 8, or x is less than or equal to 8. So what does that tell us? Well, my values have got to fit between 5 and 8 inclusive, so the maximal domain, or the implied domain of this, would be between 5 and 8, and square brackets, inclusive. So that's a handy little trick. Just look at each of the functions and decide which bits can't be 0. Another quick hop, skip and jump is something called a hybrid function. Right? Well, if you think of a hybrid car, what do we know? Well, a hybrid car can take electricity and gas. So it means it can be more than one thing. And a hybrid function is pretty much that. At this moment in time, a straight line, something like y equals 2x plus 1, is not a hybrid function. It's a function, and we can even now go on to say, well, it's a one-to-one function because there's only one y value or one x value for each y value. But if I had something looking like this, where I had a straight line and something like that, and then maybe, oh, I don't know, a curve, which would be highly unlikely, this here would be a hybrid function because the graph is split up effectively in different functions, all joined together. Difficult to think of a real-world example, but if the graph looks like it's moving around, or if the graph looks like it's breaking, or there's joints, then it's going to be a hybrid function. These are generally given by something along the lines of f of x, and you'll have curvy brackets and a number of functions where they will tell you that it exists only between certain values. So x is less than or equal to 0, this might be 0 is less than or equal to x is less than or equal to 1, and then a half of x plus a half between or for x is greater than 1. So we can pretty much see now that this function is only defined for values less than 0 and not including 0. This function is for values including 0 and 1, and this is only going to be used for values of x greater than or equal to 1. Sometimes it's important to know the sums and product of functions. If you have two functions, say f of x and g of x, then if you want to sum them together, which is f plus g of x, that's the same as f of x plus g of x. And if you want to find out fg of x, which is when you are multiplying them together, then that's the same as f of x multiplied by g of x. Something to note is that the domain of both f plus g and fg is the intersection of the domains of both of them, right? So these are only valid for the parts of the domains where they intersect. And as a quick example, if we have f of x is equal to the root of x minus 2, then we know that x has to be greater than or equal to 2 for this thing to work. And if we have g of x to be the root of 4 minus x, then we know that x has got to be less than or equal to 4 for that to work, otherwise we end up with negatives again. So we now know that the domain of both of these, alright, so the domain, and they use dom, of f and, or intersected with the domain of g, alright, the numbers that apply to both of them will actually be between 2, 4, right? Those are the only numbers that work. Nice quick example, but something that I have definitely seen in a VCE past paper is the idea here, alright? So you need to remember that when you add or multiply functions, then it's only going to be valid where the domain of the first function intersects or and with the domain of the second function. One of the great, if not somewhat confusing, sections of chapter 1 seems to be the one dealing with composite functions. And a composite function is literally where you have one function which outputs and goes into another, right? And this has been written as h equals g o f, for example. Now h equals g o f means we have a composite function which is made up of two other functions. And for simplicity, what I view this as is that the output of f goes into g. Right? So if we have, for example, f of x is equal to 3x plus 2, and we have g of x is equal to x squared, then h of x is given by g o f, which means that f goes into g. It means that function gets substituted into there. So where we see an x, we're going to write 3x plus 2 and square it, and that is our h of x. Now in many cases we need to know whether these things are defined or not, and the way that we can work out whether it's defined is by using a bit of a trick, as it were, or just some general knowledge. Now g o f, or g of f, right? We are looking for, and this is where you should learn this, and specifically which way it goes around, if it is defined, if a function or a composite function is to be defined, because sometimes you can put one thing into another and it just won't work, then what they say is the range of f has to be contained within the domain of g, right? So it is the range of the second one is contained in the domain of the first one. So if I had FOG, well, I'd have fog and I probably wouldn't go out in my car because it would be too dangerous. Then what I'm saying is we're looking for is the range of G contained within the domain of F, right? So first things first, that's quite useful to know. Something else that's important is when questions will say to us, well, if the composite function is defined, i.e. the range of G is contained within the domain of F, then they will then say to you, well, what is the actual domain? What will the domain of the function be? Well, if the range of G is contained in the domain of F, FOG then would suggest that the domain of that, if we're dealing with FOG, then the domain of FOG would be given by the domain of G. It's this last letter here. And in the same way that if I was looking for the domain of GOF, and it is defined, then that would be the same as the domain of f. If we look at a quick example, imagine we have the functions f of x is equal to 2x minus 1, and we have g of x is 3x squared. A nice quick table for each of these functions. If we have our g and we have our f, and we look at domain and range, because remember the trick that we're going to use in a moment, or the information that tells me whether something is going to be defined, will require us to know the domain and ranges of each of these functions. Well, if we look at our g of x, what is the domain? Well, any number can go into this in terms of x, so that's real. And what do we know about the range? Well, for a standard x squared curve, then it's going to go from 0 to infinity. Okay, that's one way of writing it. Or another way we could write that is our positive real values, but and including 0, right? Because our positive real values doesn't normally include 0. What about our function f, or our f of x? What is our domain? Our domain is, well, any number seems to go in and any number seems to come out. So let's see, is fog defined? Well, if we go back and just check our previous knowledge, fog, so we've got to have the range of g and the domain of f. So that is given by the range of g has got to be contained in the domain of f, and let's just see g o f, that would give me the range of f has got to be contained in the domain of g. Well, is that actually possible? Well, let's just see. The range of g, so where is the range of g? This one here. Is it contained in the domain of f? Well, yeah, because these are all real numbers, and this is just a subset, so we now know that that is defined. What about the other way around? Well, is the range of f, which is real numbers, contained in the domain of g? Yep, that's also given by. So, yep, we can see that they are both defined. And if I wanted to find out what the domain of fog is, remember the domain of fog will be given by the domain of g, this function here, and the domain of g is real numbers. And what about the domain of GOF? That would be given by the domain of f. Okay, so the domain of f, and what is the domain of f? It is also the real numbers. Seems fairly simple. Let's have g of x is equal to 2x minus 1, and we'll have f of x equal to the root of x. We'll draw a quick table. All right, so we've got our domain, and we've got our range, and we've got g, and we've got f. So let's see. What is our domain of g? Well, that seems to be real values. And what about our domain of f? Well, that would seem to be only the positive real values, including 0, I think. And what about our range of g? What values will come out? Well, likewise real. And what will our range be here? Well, I think anything, again, from our positive real numbers, including 0. So how do we test whether GOF is defined? Well, GOF is the range of f contained in the domain of g. And while we're at it, let's just see FOG would be the range of g contained in the domain of f. Let's see, so the range of f. The range of f is positive real numbers, including 0. The domain of g is that, included within that. Yep, it is. So as far as I'm concerned, GOF is defined. Let's just check about FOG. Is the range of g real numbers contained in real plus? Is this a subset of this? No. This is obviously all of them. This is only part of them. They don't. So that is not defined. What would our domain of this function be? Well, the domain would be equal to the domain of f. And what is the domain of f? Well, that would be the positive real numbers, including 0. And if they wanted to come up with the actual function, how would we do that? Well, if I wanted to find the function of GOF, that is saying f is going into g. So that would be g f of x. So where we are seeing our function f of x, that's going to become 2 root x minus 1. Right? So that would be our composite function there, which would be 2 root x minus 1. I'm just substituting the f of root x into there where I see that x. Right? So it's just an idea to remember this stuff, in specifically about how we define functions and which way this range and domain goes. The next section of the textbook looks at functions of the form y equals f of x with a modulus outside and y equals f mod of x inside. If you are looking for the function of x is given by the mod of x squared minus 4, then we would know that basically if we were to draw this without the modulus sign, you'd get a graph looking pretty much like this. Yeah, well, this would cross through at -4. Well, when you take the modulus, if you remember, all x values turn positive. And more specifically, what they say is this part of the graph here, this bit below the x-axis, just reflects up. And what you would end up with is that there, going through +4. So if I was to draw that graph, quote unquote, properly, you would get this, and then this, and then this, roughly speaking, and I mean really roughly speaking. With this situation where you have the modulus inside, then it becomes a little bit easier, because what you do is you only draw, or you reflect, what is in the positive x onto the negative x. Does that make any sense? Well, if we have something along the lines of y equals the mod of x squared minus 2 mod x, right? What they're suggesting is you can write this or think of this as the graph of y equals x squared minus 2x, which would generally speaking look like this. All right, so it'd look like that, but what you do is you ignore this part of the graph. All right, that part of the graph can be ignored because of the modulus signs, which are here and here. And what you find is the graph actually reflects. So this bit here reflects in the y-axis to be here, and nothing more to it. Told you this can be a quick leap through chapter 1. We're now finishing with inverse functions. An inverse function is effectively a function that is reflected in the line y equals x, right? And when you actually do this mathematically, you either do it graphically or you just have an equation where you replace the y and the x and just inverse it. One of the things you need to realize is that when you are inversing a function, that if you have a function called f of x, the inverse is written as f to the minus 1 of x. And what you find is if you have the domain and range of the original function, they actually swap, and the domain of the function becomes equal to the range of the inverse function, and vice versa. The range becomes equal to the domain of the original function. So that's something interesting to know. If we look at a bit of an example, then if we have the function of x is given by 2x minus 3, and we're looking to work out its inverse, well, this at the moment is y is equal to 2x minus 3. That's the original function. Well, if I want to work out my inverse function, then I swap every x for a y and every y for an x. So the inverse function, so f to the minus 1 of x, will give x equals 2y minus 3. So we'll now rearrange that, become x plus 3 is 2y, or y is given by a half of x plus 3. You just rearrange it. So if our original function is this, it's 2x minus 3, then my inverse function, f to the minus 1 of x, is given by a half of x plus 3. Right. What is the domain of this function? Well, it's real numbers. And what is my range? Well, real numbers again. So in this situation, my domain and range will both be real, because what would be the point in swapping them over? In fact, if you swap them over, you get exactly the same thing. Now, this only works with one-to-one functions, right? This only works with one-to-one functions. But questions may try and trick you. If we look at the example in the textbook, then they're suggesting that if you have a function of x is equal to 1 over x squared, then automatically we should be looking at this and going, oh, that's not a one-to-one function. Why? Very quickly, draw a sketch, and if you remember, the graph of 1 over x squared basically looks like that, which if we draw our horizontal line through, we notice that for each y value, there is actually more than one x value, so that's not one-to-one. What we can do is we can put on this what they call a restriction, right? We can actually say, well, we're only going to look at part of the graph. So if I was to place a restriction on this and say, well, f1 of x is equal to 1 over x squared, but only for x values greater than or equal to 0, then what can we now see with regard to this function? Well, what is our domain going to be? Well, the domain for this is going to be the values here that are possible for x. Well, it would be from 0, but not including 0, through to infinity, not including infinity. And what would my range be? Well, what would the values be? Again, 0 to infinity, but not including. So if we now say, well, let's restrict our function to this particular instance, then I can now go on and find the inverse of f to the minus 1, function 1 of x, by using the idea that, well, if y was 1 over x squared, then the inverse becomes x equals 1 over y squared, or y squared is 1 over x, and so y becomes the root, positive and negative, of 1 over x. Okay, that seems fairly interesting, which is equal to plus or minus 1 over the root of x. So, what would that now mean that my domain and range would be? Well, if you remember, the domain of this inverse function is equal to the range of the normal, so the domain would be between 0 and infinity, and likewise my range would be also between 0 and infinity. Now, that might come over as a fairly trivial example, but the fact is it just highlights the fact that we can have a restriction. That's pretty much a gallop through Chapter 1, Functions and Relations. Hopefully some of it's now a little bit more clear. We'll see you on the next video.